All right, welcome everybody. My name is Eric Novick. I'm your host. Today's talk is the introduction to nonparametric Bayes, and we are lucky to have Arman Argasian. I hope I didn't mess that up. Joining us. Welcome, Arman.
Hi, Eric. Thanks for having me, and hi, everybody.
Cool. So let's jump into your background a little bit. So you majored in math at Providence College and then went into biostats at the University of Pennsylvania. So what attracted you to biostats, and how did you settle into this nonparametrics stuff, which I think is somewhat unusual for biostats?
Yeah, I actually majored in this particular track, the quantitative economics track at Providence. I did get a math minor, but I think doing QuantiCon got me interested in statistics. I went to work at an economic consulting shop, and after that, did my PhD. And I'm doing my PhD now, and I worked with Jason Roy, and he had a grant out at the time developing some nonparametric Bayesian methods specifically for causal inference problems. And it just sounded really interesting to me, mostly because of the computational aspect of nonparametric Bayes is something that particularly appealed to me. But it was really at the intersection of a lot of things that I liked. Doing a good dose of causal thinking, really flexible modeling, and then thinking deeply about computational efficiency. And so nonparametric Bayes just had a lot of things that I liked doing.
So then you mentioned you went to the industry. You worked in health economics, right? And before coming back and doing your PhD in academia. So I'm curious, what are some of the differences between, the I assume kind of researchy things you were doing in industry and the things you're doing in academia today?
So if I were to describe the main difference, I think, so I liked both. I liked working in industry a lot, and I had the opportunity to work with a lot of PhDs and MBAs and just a lot of people from different backgrounds. And I would say that the main difference is that, in industry, you don't typically have to worry about funding. You don't typically have to work on, like, at least in a consulting, working on developing new methods. You just focus on using existing methods and interesting applications that solve real problems for clients. So it's time sensitive. There's a real problem, and you have to have a good command of statistical methods that are needed to solve those problems. So you're not really devising many new methodology. I would describe PhD work as a little different in that there's less of a time crunch. You can afford to think deeper and go on excursions that may not be fruitful, and there's less penalty for that than there is in industry. And the focus is more on developing novel solutions for large classes of problems that tend to come up, rather than, at least in my line of research, rather than using existing methods, if that makes sense.
Yeah, totally.
Yeah.
So to just dig in a little bit in health economics, so it's an extremely important field, right? As it informs both like the kind of drugs that are being developed, but also how these drugs ultimately end up, in people's bloodstreams, I suppose. So what specific aspects of health economics that you're working on?
Right now, a lot of the methodology that I'm developing, most of the motivations are in specifically cost estimation, trying to estimate incremental, like, differences in costs that would have accrued under different hypothetical treatment assignments. And then also focusing on cost efficacy, right? So sometimes patients are randomized to different treatments, or maybe not randomized in observational studies and they're selected into treatments. And they might accrue some efficacy to the treatment, but then they also accrue costs as well. And so then there's a typical health economic question of, like, does the efficacy outweigh the cost? Do you want a drug that's 20 times more expensive that will improve survival by like a minute, to take a very extreme example? So those are generally called cost effectiveness analyses. So I'm interested in developing methodologies for those types of applications as well.
And so turning back a bit to nonparametrics, when we posted the advertisement for this talk, and some of the questions were, wait a second, what nonparametrics? What you mean? You don't have any parameters? Which is kind of it's somewhat of a silly term. So maybe to tee up the rest of your talk, like where does that term actually mean? What does that term actually mean?
That'll be the focus of the first several slides of my talk is sort of touching on this issue of what do we actually mean, and at least in the Bayesian context when we say nonparametrics. And there, you're right, like it's a word that's used in many different ways in statistics, and different people define it differently. Like it's not that there aren't parameters, it's that you might have a very high dimensional set of parameters, that's growing with the sample size. And in fact, you might have many more parameters than you have data points. And then the question becomes, how do you select priors that behave nicely in those high dimensional settings? So it's not that there aren't any parameters, you just introduce a ton of them to give you more degrees of freedom and more allows your model to be more expressive.
Yeah. Got it. Okay, so with that, why don't we jump into your talk now? If people have questions, please post it on the events chat or stage chat. We'll be monitoring for those. We'll let Arman go through his presentation and we'll address the questions at the end. So Arman, take it away.
Sure. So yeah, I mean, I'll devote a large part of this talk to just introducing everyone to nonparametric Bayes and trying to lay out a foundation for everyone, and maybe not getting too deep, but deep enough to give you a level of intuitive familiarity so that if you want to go out and explore the literature, you'll have some basis and some foundation for doing that effectively. And I will go over one data analysis example that I feel really happy about as a sort of a demonstration. And just as a plug, so I have a Twitter account called Stable Markets. It's I guess a reference to my former days in economics before I got into statistics, but you can follow me there. I tend to tweet almost exclusively about causal inference and nonparametric Bayes. So I'll go over different aspects about nonparametric inference from a Bayesian perspective, talk about what we mean by that, go over some examples of nonparametric priors, ones that I think maybe most people will only have heard about. I'll also talk about Dirichlet process mixtures and how that can be applied. I think a good place to start off is this very canonical problem in statistics. It's something that is an abstraction of a problem that we encounter in Stats 101, which is how do we estimate a distribution? How do we make inferences about some distribution G after having observed data or realizations coming from that distribution? What we typically do, especially in parametric settings, we might say, well, G, we want to make some restrictions about it because G, if that can just be any distribution, that's a very large class. And so we impose some structure on this distribution. In this example here, I've indexed G by some parameters omega. And so one example could be this Gaussian distribution. In this case, omega is just the mean and the variance parameter. And now we've really reduced the dimensionality of the problem, right? And we're not just estimating any old distribution, we're estimating a particular member of the Gaussian family. And this really simplifies the problem, because now if you're a Bayesian, what you really need to do is just have a prior over these parameters. And then once you have a prior over those parameters, that induces a prior over the distribution G, right? And then that will, through Bayes' rule, give us a posterior. And then we can use that posterior to make inferences about G or any type of characteristics of G. But to do this, very standard thing that I think we do in common parametric models, we've had to make this restriction. We've had to impose this pretty harsh structure on G, that it's a member of this two-parameter Gaussian family. And one way to understand nonparametric inference is that we're trying to break away from those restrictions and consider a priori a much broader class of possible options for G. One way to sort of visualize that is through this picture here, right? So we have the space of possible distributions here, curly G, and what we're really doing in a lot of parametric models is we're putting a prior over this pink set here, right? This is the space where all the Gaussian distributions live. So just give me a mean, give me a variance, and then it'll throw a point somewhere in this set here. But of course, if this is what we're putting prior weight on, then we're ruling out distributions like this blue distribution out here that is not a member of the Gaussian family. And so one way to understand nonparametric priors or nonparametric inferences is that we really want to consider a priori a much larger set of this distribution, not being restricted to this smaller set. Another way to see this is by again considering another canonical problem, which is the regression problem in statistics. So say we observe some scalar outcome y, and then we have all these features. In this case, we stuff all those features into this vector x, and maybe we're comfortable with this normality assumption and this homoscedasticity assumption here. So we're assuming common variance. But what we really want, the target of our inference is the regression function, right? The conditional outcome mean. And we want to model this very, very flexibly as a function of x. And so how do we make inferences about this function, about this regression function? And again, the typical parametric approach would say, well, I'll restrict this large class of functions into a smaller set, maybe governed by a few parameters. And once I've restricted the functional or the functional form, I've reduced the problem to a lower dimensional one. I've reduced the problem of like estimating this big function to a matter of just estimating a few parameters. So in this case, I have the example where f is subscripted by omega, which is the regression parameters in this linear additive regression, right? So x here contains different features, and I've multiplied it with a parameter vector. So changes in x correspond to linear effects on the conditional outcome mean, and then the effect of multiple covariates are additive in these omegas. And then again, the usual thing, right? So now we just need a prior over omega, and then that induces a posterior over the function itself. So if we put like a Gaussian prior on omega, we might get the typical ridge, the ridge regression solution as the posterior mean. But again, we made a very, very restrictive choice to start off with. We've restricted the class of functions to be linear and additive in x. And is that true? Is that plausible? I think for a lot of applied analyses, we might not think that is a tenable assumption, and we want something more flexible. So we really want to do inference that imposes less structure on f. And again, it's the same picture here. It's just now the pink set is the space of all these linear additive functions in x, and we want to really consider a much broader class of functions. And the question is, how do we place a prior and do Bayesian inference on such large high dimensional spaces? And that's going to be our working definition for the talk. Is I hope it's clear through these two examples that what I mean when I say nonparametric priors or nonparametric inference is really just priors over this very high dimensional and oftentimes infinite dimensional space, the space of all functions, the space of all distributions, possibly subject to some minor constraints on like the smoothness of the function, but still a larger class than, say, linear additive functions. When we're talking about parametric inference, we're talking about inference where we make restrictions on the structure, really reduce the dimensionality to a matter of estimating a handful of parameters that completely determine the object of interest. And so why do nonparametric inference at all? Why do it from a Bayesian perspective? Well, I think nonparametric inference is important in particular when you're trying to avoid model misspecification, right? This is really important in causal inference. Someone said in our reading group, I forget who, but they referred to this as like the great tragedy of causal inference is when you select all your confounders, you measure them, you include them in your model, but then you mess up the functional form. And this is something that's very tragic because you were so close, to getting good, accurate causal estimates. And so you can sort of view nonparametrics as a way of trying to reduce the chances of model misspecification. In terms of why take a Bayesian approach, because you might say, well, okay, I know how to estimate distributions. We have kernel density estimators in the frequentist literature. We can use the empirical distribution. Certainly, I know how to estimate flexible regressions using nonparametric frequentist methods. So we can have a kernel regression. And I think what Bayesian nonparametrics adds is it takes the flexibility of these classical approaches, these classical nonparametric approaches, and actually allows for full posterior inference, for uncertainty quantification, for things like principal shrinkage that you can really reason about. And I'll give examples of that in upcoming slides, but I do think that this shrinkage is important because the benefits that you get from that and the interpretability is really something that Bayesian nonparametrics excels at. And of course, uncertainty quantification. We can get uncertainty quantifications over very abstract objects. In a lot of common nonparametric frequentist models, getting point estimates is often very easy, but then uncertainty estimation becomes very difficult. You have to do things like in parametric settings, for instance, even you have to do things like delta method if you want a posterior over transformations of your parameter of interest. Well, Bayesian inference is nice because the uncertainty quantification just becomes a little more automatic once you have a full posterior. There are many of these nonparametric priors over abstract objects. So remember, in nonparametrics, we want to break away from linear additive functions and consider just functions broadly. We want to break away from Gaussian distributions and focus on distributions in the abstract, right? So there are many priors over these more abstract objects. So there are these Bayesian Additive Regression Tree priors, and here abbreviated as BART, over tree functions. So we can construct priors over trees. We can construct priors over partitions that are used in clustering problems. I saw in the chat that some people had experience with these Chinese restaurant process models. So that's great. Hopefully I don't bore anyone. There are these Dirichlet process priors that are actually prior distributions over probability distributions themselves, which is a little crazy to think about if you're just familiar with parametric Bayesian inference. And of course, we have the well-known Gaussian process prior over functions, a larger class of functions subject to some continuity constraints. We have gamma process priors it's a canonical prior for non-decreasing functions. So it's useful when you're trying to model cumulative hazard functions in survival analysis. And there's just a huge list of these priors. And I want to focus on just these first two as examples of how nonparametric priors work. And then I'll focus on application that's really using this Dirichlet process prior. And we'll see that maybe some of these priors are actually related. Bayesian additive regression trees is the first one that we'll consider. So BART, you can view this as a prior over tree structures. We're all familiar with regression trees. And so you may have seen tree structures like this when learning about regression trees. Here I've denoted this tree as TJ. And what does this tree structure TJ consist of? Well, it consists of a few different things. It consists of these nodes where we make splits on the data according to some splitting variable and some splitting threshold, right? And then it also consists of these terminal nodes. So if you give me a covariate x1 and covariate x2 and these parameters, these thresholds, and these terminal node parameters, these etas, I can drop down a subject's covariate vectors and they'll land in one of these terminal nodes, and I can assign to them as a prediction these eta values. And that's typically how regression trees work. What is different about Bayesian additive regression trees and this BART prior is that the tree is generated randomly. All right, so we might pick which variable to split on uniformly at random over the set of possible variables, and then out of all the different values for that covariate, we might randomly pick one to split on. And then once we get to one of these terminal node parameters, we can now specify a prior distribution to draw these terminal node parameters from. So let's say all these terminal node parameters are coming from some distribution, let's say Gaussian distribution. So what distinguishes this from a regression tree is that the tree is generated randomly. How do you know when to stop growing the tree? Well, there is also a prior on the tree depth, and here denoted by D. So we can sort of ignore alpha and beta for the moment. There are tuning parameters, but what's important here is that the probability that any node at a given depth D is non-terminal is given by this quantity here. So if you're at a node at a very, very high depth, right, this probability is close to 0, which means that the probability of that node being terminal and you're not going to grow the tree any further is near 1. Right, so really this prior on the tree depth is shrinking towards shallow trees. Now, this is the second distinguishing feature that we've covered about BART. In typical regression trees, we rely on some post hoc pruning to like prune back the trees that are grown too far, and that's our primary mechanism for avoiding overfitting. We see that in the Bayesian approach, we actually have a prior on the tree depth that says, we can allow this tree to grow and grow and grow to accommodate the complex structures of the feature space. But we're going to have a prior that actually favors shallower trees. So that informative prior is going to shrink us back and prevent overfitting. So this is a probabilistically principled way of generating random trees, is through a BART prior like this. How can we use this for regression estimation? Well, BART, the method sort of follows from considering m such trees, denoted by fj here, and it denotes and it envisions the regression function as being a sum of these m trees, hence additive regression trees. Right. So here fj just simply maps a covariate vector to one of the terminal nodes in the jth tree. And then it adds up all those values together, and then that's your regression function evaluation. And the way that this works in terms of computation and posterior inference is typically through this approach called Bayesian backfitting, where you sequentially update these M trees one at a time using the residuals from the previous tree's fits. And you use like these really interesting Metropolis style updates where at every iteration of the sampler, you propose to change the tree, like you might propose to grow the tree, and then you have some Metropolis rule for accepting or rejecting that proposed move in the tree space. And so sometimes putting all this together, sometimes we denote this as a BART prior. So we might say that f follows a BART prior, which is just to say that if it's a function that has a functional form of a tree where we have priors on the splitting criterions on the terminal node parameters and the prior that I just showed you on the tree depth. And so putting all that together, we sometimes say that f follows this BART prior. If you go through the computation, you can check out the original paper. I think Googling it will lead you to a paper by Chipman and Ed George and everyone. I want to say it was published in Annals of Applied Statistics that really goes through the details of this. But here's a picture that shows you the fit of this Bayesian additive regression tree model on training data that is shown in gray points, and then some test data that was omitted in red. And so you can see that first, BART is capturing a very complicated functional form here. The blue line here is showing the posterior mean regression and the posterior mean regression. The shaded light blue is showing the uncertainty, the posterior uncertainty around that estimate. And you can see that the uncertainty is really increased in the area where we don't have any training data. So this is, again, going back to that idea that I mentioned earlier, that the Bayesian nonparametric approach for regression trees is giving us uncertainty quantification that is quite natural, and it has behavior that we find desirable in these out of sample areas. And also it's giving us principled shrinkage. So we're not doing anything ad hoc to prune back these trees. We're just relying on well-defined priors to shrink towards shallow trees. This is all very appealing, I think, from a Bayesian point of view. Another example of a nonparametric prior is, it comes up in the clustering literature. So consider this clustering problem where we just observe data for n subjects given by y here, so 1 through n. And we think that each of these subjects belong to some cluster with the cluster indicator given by ci here. And if we only knew the cluster that this person belonged to, we know that their observation is drawn from a Gaussian distribution with a cluster-specific mean. The issue is that we don't know these means and we don't know the cluster membership, right? We just have this vector of data points. And ignoring the question of how to estimate these means, and we could also be flexible about these variances here, but I just want to ignore that and focus on how do we make inference about the cluster indicators? How do we actually do clustering? Well, we need a prior over this vector. And again, this is a high dimensional problem. Like BART was a high dimensional model, right? Because we had all those terminal node parameters. We had many regression trees that we were adding together. I think the standard BART model added 200 trees together. So it's a very high dimensional model. And this is also very high dimensional because we have as many cluster indicators as there are subjects. It's not even factoring in the mean and variance parameters that we're trying to estimate. So it's very high dimensional, and we need some way of specifying a very flexible prior on these cluster indicators. Another way of saying this is we want a prior over a partition, right? Because so let's say there are only 5 unique clusters here and everyone belongs to 5 mutually exclusive clusters, in the sense that these cluster indicators are defining a partition of these subjects into mutually exclusive groups. So one such prior is the Chinese restaurant process prior. So it just factors out this joint distribution into a sequence of conditional distributions. So subject i's, or subject 1's cluster membership, subject 2's cluster membership conditional on subject 1, subject 3's conditional on subject 1 and 2, etc. And the way that the Chinese process defines each of these terms of this prior is through the following mechanism. It says, well, the first subject, we'll just assign them to cluster 1. For each subsequent subject, there are 2 possibilities. The first possibility is that the subject could belong to a cluster in which one of the previous I-1 subjects belong to. And with what probability? Well, probability proportional to however many patients out of those I-1 subjects actually were in that cluster to begin with. So by the time this subject I comes around, if there are many people in, say, cluster 1, then I have a higher chance of also belonging to cluster 1. But there's a second term here that says, well, I'm also going to allow for the a priori chance of belonging to a cluster that I've never seen before. So none of the I-1 previous subjects belong to this cluster, but I'm still going to allow for a priori probability of belonging to this new unseen cluster. So the reason this is sometimes we make this Chinese restaurant process analogy. I forget what the story was behind this, but the metaphor is as follows: like you have this restaurant and it has infinitely many tables, and each table can seat infinitely many subjects, and the customers are arriving one at a time to the restaurant. And so when a new subject arrives, they can either be seated at an existing table that's occupied, so that's this first term here, with probability proportional to however many people are already seated there, or they could choose to just, if they're loners, just sit at a new table that no one is sitting at. And this is a really useful prior process to define on partitions, because we're not making, I won't say any, but we're not making much restrictions on how many clusters there are, right? In principle, there could be everyone could get clustered into their own unique cluster, and so we'll have n clusters with n subjects. So in that sense, we're upper bounded, but it's not like k-means where we're saying, okay, there are no more than 5 clusters. We're allowing the clustering to be adaptive. And if you get a very, very complicated data set, you might have more clusters forming. If you have a very homogeneous data set, you might not have any clusters form at all. So it's data adaptive in that sense. What's also interesting is the nature of this prior actually favors fewer clusters. It's not very common that you would have everyone clustered into their own degenerate cluster. And that's because as your sample size is growing, And as I tends towards an n that is larger and larger, this term gets close to 0, right? So the probability of being seated at a new table is getting smaller and smaller and smaller. This is sometimes called the rich get richer property of the Chinese restaurant process. And this is very distinct from how typical frequentist methods handle clustering, which is to say, okay, well, we might do something like k-means, and we might run k-means with different k values and then compare them with some ad hoc measure of fit, and then pick one that seems to balance the bias variance trade-off nicely. No, just like in BART, here we're allowing for the clustering to be very, very flexible, but we're going to have a prior that favors fewer clusters. Just like BART, we could grow these trees very long, but we're going to have a prior that favors shrinkage towards shallower trees. Hopefully that's clear. I mean, sometimes people write this as just the cluster indicators following a Chinese restaurant process with a tuning parameter alpha. In all these cases, I think the takeaway is that in parametric phase, we have low dimensional models, and we're drawing the parameters, these low dimensional parameters, from very standard probability distributions. When we're talking about nonparametric phase, as we saw with Bayesian additive regression trees and with this clustering problem, the model is characterized by a very high dimensional set of parameters. And now in terms of priors, we're going to have to, instead of relying on standard distributions, we're going to have to rely on stochastic processes or a sequence of random steps that when we take those steps will generate this type of object that we are interested in. So we'll generate a random tree, we'll generate a random partition. So with that, I'll turn to an application to medical cost modeling. So this is a real data example from this plot here from a collaborator. I asked her, could you give me an example of some medical cost data that I could put in a slide? And she sent me this histogram of emergency department expenditures. And you could see the characteristic features of medical cost here. There's this huge spike at 0. Just some people never have emergency department visits, and so they have a lot of 0 costs. And they have a long tail and then there's a long tail to the cost distribution. Similarly here, this is another applied project from a clinical collaborator I have doing cystic fibrosis research, and they sent me this histogram. Again, you see a large spike at 0 costs and a long tail, and you can even detect some multimodality here, right? There seems to be some moderately cost subjects. There seems to be a tail of high cost subjects here. So these are very, very complicated outcome distributions to try to model. This is from an example from the literature that I had grabbed of just people trying to do clustering on cost data. So this is like pre and post treatment costs on the X and Y axis respectively. And the colors here indicate, I think, some k-means clustering assignments. And so people are interested in detecting clusters of patients who might be very low cost or high cost, and trying to understand what's driving this heterogeneity and costs. So in terms of some notation, what we typically observe in these settings is this data set given by an outcome, a cost outcome Y, and some covariates, a vector of covariates. And in a causal setting, you might think of some treatment, so binary treatment, maybe people getting assigned to do 2 different treatment arms, and some confounders that influence both the treatment and the outcome. We won't really talk about causality here, but you can just think of this as, a feature vector. One way of handling cost outcomes is this type of what is often called like semi-continuous or a hurdle model, where that explicitly accommodates for those structural zeros, what I'm calling zero inflation here. It's not what I'm calling it, but it's termed zero inflation in the literature because you just have many, many more zeros in this distribution than you would expect from standard distributions. And so this is really capturing that, because it's saying with some probability pi, cost can come from the point mass distribution at 0, and then with 1 minus that probability, cost might be coming from some other distribution. So this could be like a gamma, a log normal distribution, or you could, I guess, even specify a normal distribution here if you just want to estimate a mean and your costs are sufficiently high. Probably normal distribution here would be okay too. The point is here that there's like a 2-point mixture here of a point mass at 0 and then some positive, a distribution on positive cost values. And so this probability of cost being zero is itself governed by some logistic model. So X transpose gamma here might be coefficients in logistic or a probit model. And then this distribution here is governed by parameters theta. And so we're just going to we'll call all these parameters here omega. And then, yeah, so this could be either the logit or the probit link. It doesn't really matter. People tend to use either. And so if you specify this distribution here, this positive distribution to be normal, then the regression that you would get from that is maybe this linear regression where beta is your regression coefficients, and then phi is the variance in the normal distribution. Or you could specify something with a log normal, in which case the regression has a different form. Now we know that in log normal, the mean and the variance are coupled, right? So the regression might have this form. And so this is the method that people typically use when they model zero inflated data like costs. But it's still undesirable for a few reasons. I mean, one is, again, this is a very restrictive structure. Are the covariate effects really linear? Are they really additive? We could include interactions in this vector X, but then what interactions should we choose to prevent overfitting? If we're going to do something like splines, like how do we choose the parameters of those splines? How do we capture multimodality in the cost distribution? And will this actually do a good job at capturing the skewness that we saw in those histograms? I mean, there's very good reason to think with cost distributions like the ones I just showed you that these parametric assumptions are untenable, and we want something more flexible. So, of course, to take a Bayesian nonparametric approach, we're just going to go high dimensional, move from a single parameter for all subjects to subject-specific parameters. Subject-specific parameters that govern the probability of cost being zero. So now you see that gamma is subscripted by I here. And we also have subject-specific parameters governing the positive cost distribution here. But then we've introduced these high-dimensional parameter vectors, these omegas, but then we need a prior over this. And so we might think that all of these are jointly following some prior distribution G, but then what are we going to do about G? How do we specify a reasonable prior for G without making restrictive functional forms about its nature? And one such nonparametric prior on distributions is called the Dirichlet process distribution. So you can think of the Dirichlet process as a stochastic process that generates random probability distributions, right? Just like BART is a process that you follow to generate random trees, just like the CRP is a random process that you follow in sequence to generate a random partition, there is also such a process that you can follow to generate random distributions, G, from this Dirichlet process. And these distributions that you generate are in some sense centered around a mean distribution G0 that you're going to have to specify, and the variability of those distributions that are generated by that process are going to be governed by this alpha parameter. So the most important thing is that the distributions that we're drawing from the Dirichlet process are discrete, and that'll come into play when we talk about clustering. But for now, so we can think about this GIF here. This GIF visualizes what draws from a Dirichlet process look like. So I'm playing it here. And so each black line here is a realization of the Dirichlet process in terms of the CDF. So this is the cumulative distribution functions that are being drawn from the Dirichlet process. And they're sort of centered around G0, which I've picked here to be a Gaussian distribution for illustration. And we see with higher values of alpha, the realizations are tighter around the prior mean distribution. So this is nonparametric in the sense that the cumulative distribution functions that we're drawing, yeah, they're centered around the Gaussian distribution, but they can have very wild functional forms. Like they can actually capture very flexible types of distributions. It's just that they're anchored towards a normal. And then the other thing you can see here is just the stepwise nature of these CDFs. That's a consequence of the discreteness of these distributions that I mentioned. So it's very clear here that these are not continuous distributions. So the parameters that are governing this zero inflated regression, remember we had called those omegas. It can be shown that if these omegas are following a distribution G, and G follows a Dirichlet process, then that induces what's called a Polya-Ern prior on the parameters governing our regression. And this should look very familiar to you from the Chinese restaurant process discussion, because what this is telling us is that the ith subject's parameters, well, it could equal any of the previous I-1 subject's parameters with probability, with probability proportional to 1, or with probability proportional to alpha. It can be a totally new parameter that you have not seen in the previous, for the previous I-1 subjects. So in other words, like, this is the discreteness of the Dirichlet process coming in. And it's also closely related to the Chinese restaurant process clustering, right? In fact, like, we can view subjects who share the same parameters as being in the same cluster. So all these stochastic processes are sort of related mathematically, and you could sort of go back and forth between some of them. And I'm alluding to that relationship here. Of course, in the posterior, there will be data coming into here that drives posterior clustering. And what will happen is that patients who have very similar regression parameters in terms of their data will cluster together, and then patients who have very different ones will have separate they'll be modeled with a separate regression, such that the overall regression is like a mixture of these cluster specific regressions. And so how do we do inference on this type of a model? Well, we can use the clustering that we just discussed here, and actually introduce these auxiliary variables, these cluster indicators, and then have an MCMC scheme that iterates between updating the cluster indicators conditional on parameters, and then updating the parameters conditional on the cluster indicators. So this is very typical in mixture models. If you're familiar with mixture models, like this type of idea comes up a lot, and it's also very similar to the EM algorithm that people use for MLE estimation. The central idea is that there are these auxiliary variables that we wish we had that we don't, but if we had them, it would simplify the likelihood. And so we just introduce those and then have this two-step Gibbs procedure here. And that'll output draws of both the regression parameters for each subject, as well as these cluster indicators, which we can use to look at different subgroups of the data that might be interesting. So here's the MCMC process playing out in real time rather than writing it out in formulas. I've just made a GIF here that'll run through this. So I've initialized the MCMC to start with one cluster. On the left panel here, you see the observed data, and you'll see colors indicating clusters. So you'll see that this is a complicated data set. New colors will emerge, or new clusters will emerge to accommodate that complexity. You see that we have zero inflation here. These are the predictions at every iteration, so posterior predictive draws at every iteration. And so as the iterations proceed, you'll see that the posterior predictive draws look more and more like the data as the model fit is improving from iteration to iteration. So here we go, and like a green cluster here is popping up. The colors don't really matter. What matters is which patients are getting consistently grouped together. This is due to a label switching issue, which I won't talk too much about. But I think it's cool to see this thing playing out in real time. So you can see that these subjects are getting clustered into three distinct clusters, each one with its own degree of zero inflation. So here we have zero inflated costs for the red cluster, zero inflated costs for the green cluster, and there are no zeros associated with this cluster here. And you can see that the posterior predictive draws are looking more and more faithful to the actual observed data. So I think it's cool to see these things playing out in real time. So I'll just go through a data description really quickly, since I'm running a little low on time. So we did this nice analysis using SEER Medicare data. This is claims data from Medicare, and we're looking at costs associated with radiation and chemotherapy treatments for patients suffering from endometrial cancer. So that the arousals here. And so the outcome here of interest to the clinical collaborators is total inpatient costs accrued over 2 years. And these cost distributions were pretty wild, lots of skewness, lots of zero inflation. So we had about like 15% of the costs in the chemo arm were zero, for instance. And then we had a lot of covariates on each subject, like their cancer stage, comorbidity index, the CCI, tumor grade, et cetera. So here's a quick look at the data by arm. The model that we actually fit here is a more complicated version of the model that I presented here. I presented a more of a simplified model for the purposes of this talk, but because what we were really interested in doing was doing causal estimation, actually estimating causal difference in costs that would have been accrued under different treatment regimes. But I want to focus more on predictive aspect of the modeling, just the model fit in general. This, let me zoom in here because it might not be so clear. So on the x-axis here, or on the y-axis are the quantiles of the observed cost distribution, right? And then on the x-axis are the quantiles of different predictive draws of our model. If our model is capturing the data distribution really well, then the predictive draws should have a distribution that is pretty similar to the observed cost distribution. Hopefully, we see that a lot of our posterior predictive draws are faithfully capturing this data because our posterior mean here is along the 45-degree line, right? So we also fit a BART model for these costs. And what we saw with BART was that although the mean of the distribution might be doing pretty well, it really has a trouble capturing the skewness of the distribution. So here it's consistently under predicting costs. And that's for different reasons that we could get into. This is the gamma hurdle model, so the parametric model. You could see that it does a better job at capturing the skewness, like at the high end of the distribution here, the draws are closer to the 45-degree line, so it's more faithful to the observed data, but it's not doing as good of a job as the zero-inflated model. And the reason for that is just because of the adaptive nature of the Dirichlet process. So here we see, here I plotted the total costs on the y-axis against household income. And here, these colors indicate the posterior mode cluster assignment under the Dirichlet process to give us a sense of how the Dirichlet process is chopping up the data, how it's partitioning the data, at least on average across MCMC draws. And what we see is that there are these clusters of patients with, say, low costs in red and green, and there's some cluster of patients with moderately high costs, but then there are also these patients here in light blue that have extremely high costs. So much so that the Dirichlet process is actually introducing a separate cluster to accommodate them and really provide a good fit on the tail of the distribution. And we could see that on this axis here, this is just cost distribution plotted against comorbidity index. And we could see that these orange patients, not only do they have a little higher cost, but they also tend to be a little sicker. Like these red patients, on the other hand, they mostly have a CCI of about 0. What is particularly useful about the clustering and the Chinese restaurant process style clustering that's induced by the Dirichlet process is that we can make network diagrams like this. So each patient here is represented by a node, and the vertices connecting any two subjects is inversely proportional to how frequently they are in the same cluster together across MCMC draws. So for example, all these patients here, they're almost always clustered together across MCMC draws. That's why they're all so close. This node here and this node, they're almost never clustered together, right? That's why they're so far apart. The colors indicate like are they clustered together sort of on average, so to speak. And what's interesting is this patient here, so this patient in the posterior mode was clustered as belonging to this red group. But we can see that there's a lot of uncertainty about this person. Well, about half the time they're getting clustered in with these people, and then half the time they're getting clustered in with these people. And so we have a lot of uncertainty about where this person belongs. And this type of uncertainty quantification is something that is absent from most classical clustering algorithms. Most clustering algorithms and analyses tend to focus on the actual hard clustering assignment, and it's harder to sort of characterize the uncertainty around that. But here we can sort of easily identify which patients do we have a lot of uncertainty about, and maybe we shouldn't take this person's cluster assignment so seriously, because there seems to be a lot of variability around that. What's interesting is that these 3 light blue patients here, so these patients with high costs, they're fairly consistently getting clustered away from everybody else just because their costs are so high. The clustering is really key to capturing those high cost patients, right? It's allowing you to capture skewness in ways that typical parametric models probably don't. And if you want to estimate a distribution from a statistical point of view, you have to be able to capture the tails really well, right? And for a lot of estimates, like the tail is crucial. The tail behavior really drives a lot of the behavior of that distribution, and it's something that the Dirichlet process regression excels at. So yeah, I mean, so that's all I had. So thank you, Eric, for inviting me and letting me talk about something I love talking about, which is nonparametric Bayes. If anyone has any questions for me, I'll be happy to take those questions.
Okay, so we do have a whole bunch of questions this time, which I think is good sign. I'm not sure if we'll be able to get through all of them, but we'll try. One of the first ones I kind of want to throw out is that, I mean, these seem to be like a pretty amazing flexible methods, but what are some of the limitations of these methods that you see? Like where do you think it would break if we were too optimistic and throwing them at problems?
I see at least 2 areas where they could break. One is in high dimensional settings where you have a lot of, now, I mean, when I say high dimensional, I mean in terms of the number of covariates that you're trying to adjust for in your regression. It can get pretty complicated then, because clustering with a large number of covariates becomes very difficult. And the Dirichlet process, the standard Dirichlet process model is not very good at handling a large feature vector. So if you're doing genomic analysis, this could be a little difficult. There are modifications to a Dirichlet process, like the enriched Dirichlet process, that are explicitly made to handle these high dimensional covariate vectors. But as far as this application that I showed you, I think it'll have trouble there. In general, with these methods, especially with these Dirichlet process methods, choosing like the hyperparameters can be a little cumbersome. You have to be careful about the hyperparameters. If your priors are too tight, you might run into trouble. If your priors are a little too wide, you might run into trouble. One of the things that I work on a lot in my papers is trying to come up with good empirical ways to set priors, coming up with some good default choices for those. I think that's an active area of research, is how to come up with good. And one of the nice things about BART is actually that the default choices of hyperparameters for BART they work really well. So you can just run BART out of the box really, really well. That's not true for all nonparametric priors.
So another question, can you generally fit these models with full Bayes, or do you resort sometimes to variational inference? And in general, how do you try to validate these models if you have to do approximations?
Yeah, there are people who have come up with variational inference, and even both variational inference and also parallel MCMC methods. So if you want to do full Bayes, but you still need to scale things up, you might consider these parallel MCMC methods. And they've come up with these specifically for Dirichlet process models. So it's possible, but it's hard. The example that I showed you was full Bayes, and it wasn't that bad. I mean, it took several hours to fit with like maybe 20,000-30,000 MCMC iterations on a single chain. It could be worse. I've had worse. But again, it was a small data set. It's only 1,000 subjects with I think I had maybe 7-8 covariates in there. I think these things do not scale well in terms of the observations, and you might, for large ML production ML purposes, you'd have to probably resort to some approximation or parallel MCMC.
Gotcha. Which software, I'm just curious, you used to fit this model?
I coded these all up myself. So like a lot of these nonparametric procedures, it's hard to fit these things with things like Stan. because I work on newer methodology, there are things that I want in my models that don't exist, and so I just code the MCMC up from scratch. I use a combination of R and RCCP for efficient sort of back end of the MCMC. I do have a working version of this software. It's called Chirp for Chinese restaurant process. So you can feel free to look at that, and contribute.
Cool.
There's a GitHub page for it. But it always needs improvement. That piece of software. Yeah.
No, that's interesting. I'm just curious, is a sampler gradient based, or is it more of a non-directed exploration?
So yeah, the one that I coded was not gradient based. So it was like what I described in that slide where I introduced the latent cluster indicators and then iterated between updating the cluster memberships and then the parameter updates. So those parameter updates, you can use anything you want for those. You can use a Hamiltonian update. You can use like Langevin proposals. You can use whatever, or you can just use standard random walk metropolis. So I just chose to do random walk metropolis because it was fine. I didn't have too many mixing issues. But yeah, you could incorporate some gradient information into that step of the MCMC sampler.
Got you. So this question is from Trung, who asks, do you have any comment on the use of Bayesian nonparametric for multiple imputation? Is it better than, for example, assuming a normal distribution for the outcome?
Yeah, I think it's better. Actually, my advisor, so Jason Roy, has a paper from a few years ago called Bayesian Nonparametric Generative Models for Causal Inference, something like that. He actually dealt with this problem of we have an enriched Dirichlet process prior on a regression, and we have missing at random covariates. And the key is that you in addition to specifying an outcome model, you can specify covariate models. Under the Dirichlet process, you'll get a posterior that is a mixture of these local covariate models. And so you'll be imputing under missing at random from a more flexible mixture predictive distribution than you would under like a Gaussian distribution. So yeah, I think one of the highlights of that paper was just how well these Dirichlet process models can do if you have missing at random covariates. So you could take a look at that paper.
Cool. So this next question is from Robert Goldman, who asks, would you comment on the relation between CRP and stick breaking?
Yes. So stick breaking is, I alluded to it a bit. So stick breaking is a process that you can use to generate a distribution that follows a Dirichlet process, right? So it's one way of actually generating such a distribution. Chinese restaurant process is a little different. It's the distribution on the partition that is induced by the Dirichlet process, right? Which is different from the actual distribution itself. It's a distribution on the partition. So that's the distinction. I think I spent like a solid 4 months of my life trying to understand the difference between stick breaking Chinese restaurant processes, Dirichlet processes, and Polya-Ern processes, because they're all related mathematically, and it's at some point somebody should write something up that ties them together. But yeah, that's how I understand the distinction, if that makes sense.
Okay. Sounds good. Then a question from Kevin Van Horn. You've described the inference for CRP, but what's the actual underlying prior?
The inference for the CRP. Well, the prior is just that sequence of conditionals that tells you, a priori, I think that you have a probability of belonging to one cluster proportional to the probability, or proportional to number of people already in that cluster, and you have a probability of belonging to a new cluster proportional to that tuning parameter alpha. That's the prior. I mean, the intuition behind it is that if I think there are infinitely many groups out there, right, and I've observed so far n people from the groups, and there are, let's say, I've observed people from 6 of those infinitely many groups, and a new person walks up to me and says, guess my group. Well, the thing that I would do is say, well, I'll probably guess proportional to however many people, I'll guess each group with probably proportional to however many people I've seen, but then I know that there are infinitely many out there, so I'll just have like a small bump for the possibility that I may not have seen anyone from your group before. And so that itself is the prior, if that makes sense.
So next question from Max Livingston, which I think you alluded to earlier already, but he's asking, can you discuss computational performance? Like what are size dimensionality data set can I reasonably expect to fit a DP or CRP to?
I haven't tried fitting, like in biomedical applications that I work on. I've rarely had to deal with data sets more than a few thousand subjects. And for those, I usually could expect few hours of runtime. Again, it all depends on the mixing of the chain and your particular data set. You might have to run these things for longer if your data set is different. So yeah, I mean, I think they would run into trouble. At least these standard full MCMC approaches might run into trouble with more than a few thousand and more than like 10, 15 covariates. I've only ever done a few thousand with 10 or under covariates, and it seemed to be manageable, but I can see things getting pretty crazy after that. You would have to rely on more efficient computation than what I was doing, or doing some more approximation methods, probably, if I were to guess.
Gotcha. This next question is from Maxwell Peterson. Should I be extra concerned about overfitting when using processes like these? Also, with very permissible priors like these give, do I need a ton of data to make this get to a decent answer?
Yeah. I mean, I think these are not approaches that you would probably want to use. They're not approaches that you would want to use with like 200 to 300 data points. I mean, maybe depending on like the dimensionality of your parameter, like if you're just running a univariate regression, you might get a decent fit with like 100 people. But if you're trying to adjust for a lot of parameters, a lot of covariates, you might need a lot more subjects than a few hundred. So yes, with nonparametrics in general, like that's the catch, right? We're allowing more flexibility in the model, but we need more observations to fit these more complicated models. What was the other part of the question?
Yeah, the other one was with the very permissive priors like these give, do I need a ton of data to make this get to a decent answer?
Yeah, so the ton of data I touched on. I think the other part was the overfitting. If it is overfitting, it will be very clear. In this case, you can monitor at every step in the MCMC sampler how many unique clusters there are. And if you have 700 subjects and every iteration you have 600 unique clusters, so that almost everyone is getting clustered into their own degenerate singleton cluster, you're really overfitting, and you should probably like adjust your priors, right? So you can monitor that real time. So you should be considering overfitting. The CRP and things like BART, they do have shrinkage sort of built in, but it's a good job to monitor, come up with good quantities that'll help you monitor that.
All right. Well, I think that's all the time we have. Thank you so much for spending the time with us. Really appreciate it. I think people enjoyed it. We're not going to have one of these in December, so we'll be back in January with a very interesting talk in oncology, early oncology trials from a trialist in the UK. So again, thanks again, Arman, and thanks everyone for joining us. We'll see you soon.
Thank you. And if anyone wants to discuss more, if you have any questions, feel free to reach out anytime.
Awesome.
Thanks, Eric. Thanks for the invite.